Okay, so first, the syllabus says we have a test on Wednesday, but there's a lockdown drill on Wednesday, so we're going to push it back to Monday. So exam 1 is on Monday, and I didn't look at what the date would be. The 6th, maybe? Monday, Q6. The syllabus says Wednesday the 1st. And the topics are going to be, the kinds of problems are going to be like all of the problems that you've done up through particle kinematics. So I think that's vectors, math, and particle kinematics, including relative motion, circular motion, all that stuff. And the stuff we're going to get, the next thing we're going to get into won't be on the test. Okay. Anybody have any homework questions? Yeah. Okay, so 18. You saw what? 20 degrees. Oh, 20 degrees. Okay. Oh. You know what? That should not be in this set. That's in the wrong place. So sorry about that. Skip number 18. Yeah, so that should be in the set on kinematics, on kinetics, I mean. And so the way you would do that is oh, the angular velocity is, sorry, you don't skip it. You can do this. Does that, the 20 degrees, I don't even think, I thought you were going to have to calculate how gravity is making that work. Yeah. Right. Well, yeah, so the easiest way to do that would be to do it in a rotated coordinate system and then just re-express those vectors in the new coordinate system. Okay, so but let's first do it in this coordinate system. So we'll call this point P, this point C. Then in this coordinate system where X is parallel to the surface, you know that the velocity of C is equal to negative angular velocity times the radius, and then 0. And the acceleration of C is equal to negative angular acceleration times the radius, 0. So the omega is given, angular velocity is 20 radians per second. It's rolling down the hill, so that actually should be negative 20. So 0, 0, well, the scalar value is negative 20. And it's speeding up down the hill, so the angular acceleration is negative 15. Okay, how do you know that the angular velocity should be negative? Just physically looking at the problem, you know that that thing has to be, if it's moving down the incline, it has to be rotating clockwise, and that's negative. And then how do you know the acceleration, the angular acceleration is clockwise? Yeah, it's speeding up. If it's speeding up, there's a couple ways to think about it. You have to have agreement between the angular acceleration and the linear acceleration of the center. So that's one way to think about it. The other way to think about it is if the rotation is speeding up, omega and alpha have to have the same sign. They have to be in the same direction. So those are sort of the two ways to make sense out of that. Okay, so the velocity of the center is negative of negative 20 times, oh, and I didn't write the radius, but that's given 0.05 meters. Yes, that's right. Mm-hmm. These are all instantaneous things, so you can't take the derivatives. You can only take the derivatives if you have it expressed as a function of time. Okay, so that's just equal to positive 1, right? Meters per second. And then for the acceleration, you have negative of negative 15 radians per second squared times 0.05 meters. And that is positive 0.750 meters per second squared. Okay, so that's in the rotated coordinate system, and then I asked you to give it in the standard orientation coordinate system. The easiest way to do that is with a rotation matrix. So if you have a vector expressed in, say, a coordinate system like this, and want it expressed in this, find the counterclockwise angle theta that you have to rotate this coordinate system to align it with this one. And then your vector in the new coordinate system is equal to the cosine theta, sine theta, negative sine theta, cosine theta. times vector in the old coordinate system. In this problem, we have the vectors now, whoops. We have the vectors expressed in this coordinate system. And we want to express them in this one. So what's the counterclockwise angle to get from here to here in this problem? Plus 20. You just have to, this coordinate system, you need to rotate plus 20 to line it up there. Counterclockwise 20 degrees. So the Q matrix, the rotation matrix, is cosine 20, sine 20, negative sine 20, cosine 20, which is 0.940, 0.342, negative 0.342, positive 0.940. And so the velocity vector in the new coordinate system is 0.940, 0.342, negative 0.342, 0.940, multiplied by our velocity vector in the old coordinate system. And so you just get 0.940, negative 0.342 meters per second.
For some reason I wanted to do like the velocity of B with respect to the ground is equal to B respect to C plus respect to ground.
Okay, so that was how I just jumped right to the formulas I derived last time.
Okay.
But the way I derived those formulas was with that relative motion.
And we know this because it's
yeah, that's right. And then for the acceleration in the new coordinate system, that's 0.940, 0.342, negative 0.342, 0.940 times 0.750. I don't know what that is. Can someone calculate that? Okay. Squared. So that's the easiest way to do it. The other way you could do it is take projections of the original vector onto unit vectors in the new x and y directions. You could project the old velocity and acceleration vectors onto axes in the new coordinate system using the dot product. So the new velocity vector x component would be 1, 0, 0, dotted with the new x-axis. And you get 0.940. And to get the y-axis, you take our velocity vector in the old coordinate system, dot product with the new y-axis, which is negative 0.342, nope, positive 0.342, positive 0.940, 0. Yeah, you're right. That should be cosine and sine of 20. Yeah. So this should, of cosine and, yeah. Okay, so we're going from, here's our old coordinate system. Our new coordinate system is this. Okay, so this is our new x, this is our new y. So our to represent our new x in the old coordinate system, that's yeah, this should be positive, I think. This should be negative. Negative. But okay, so in our old coordinate system, the direction of our new x-axis is 20 degrees. And so that's the dot product with this vector. The direction of our new y-axis is this, represented in our old coordinate system. So take that dot product and you get negative 0.342. But really, with this problem, so up through the last time I taught this, I talked about rolling without slipping in a more complicated way that made this second part of the question sort of more natural. With the new way that I've talked about it, I'm definitely not going to ask you for it in a specific coordinate system. So don't worry about that coordinate system change. Don't worry about getting it in this coordinate system. Just be able to do problems like this in a coordinate system with the x-axis along the ground. So the kind of question I would ask you would be just come up with the velocity and acceleration vector in this coordinate system that I've shown here. Okay. Any other questions about that one?
Can I ask again?
That's 18, yeah.
So can we go over when we use the shortcut, the negative omega r, compared to when we use the fraction addition thing?
Yeah. So, well, with rolling without slipping, if you remember that formula or come up with some memory device that sort of where you half remember it, half derive it or whatever, that's all I want you to do. So rolling without slipping. Yeah. So 18? Okay. Yeah. Mm-hmm. Okay, let me finish this and then we'll talk about it. Anytime rolling without slipping, the velocity of the center is equal to negative omega r 0. The acceleration of the center is equal to negative alpha r 0. Let me say that's all you need. Right. So relative motion, yeah, if it says roll or rolling or rolled. So relative motion was used to derive these. So they do depend on relative motion. It's just that I already went to giving you these formulas and that's all you need. And the reason that this is the one thing where I'm just saying go straight to these formulas is because the application of rolling without slipping is a little tricky. You have to only take into account stuff that's parallel to the surface and then stuff that's perpendicular. It's just, I think it takes more time to get solid on that than it's worth, I think. So we'll just use this. Okay, what was the question? 18? Mm-hmm. So numerically I used the radius of the wheel, and then it points straight from the center to the contact with the ground, so it's just in the negative y direction. So in the derivation, so we have velocity of the point P with respect to the ground is equal to the velocity of the point P with respect to the center plus the velocity of the center with respect to the ground. Okay. Yep, that's right, because then we're just talking about circular motion. And so the r vector is this. In number 18. So yeah, I guess if the way that I did it in the solution, is a complicated way. I would recommend just doing it the way I did it here. So let's see. This is all I would ask you to do on a test. Okay. The thing with the funny coordinate system and stuff, don't do that. Just use a coordinate system. If it's on an incline, use a coordinate system with the x-axis parallel to the incline, just like you did in Physics 1 with sliding and rolling problems. Okay, let's do another rolling problem, right? That we haven't done much of that. Okay. Yes. But we're doing 16.
I mean, whatever.
So 16. Okay.
that a rolling without slipping? The cart rolled.
Yes. Oh, no, it's not.
No. Okay, that's a cart one, so maybe it's like.
Okay, so anybody want to see 16?
We don't have to.
It's not rolling without slipping, because rolling is, you use rolling without slipping to relate angular velocities and accelerations of the wheels to translational velocities and accelerations of the center of the wheel, or equivalently like the object that's rolling. This one, it just gives you the translational velocity and acceleration of the cart. It doesn't ask you for anything about the wheels. So this one is just straight relative motion. You have sort of a little Ferris wheel thing that's doing this as the cart goes that way.
We did 19
Um, okay, let me make one up.
I think we did only.
Those bicycle ones, did they give? Okay, well, let me just do a simple one. Yeah. So let's say, let's just say there's a wheel or a ball or something rolling up the hill, and it has a radius of 0.10 meters. And it has an instantaneous velocity of 2 meters per second up the incline. And an instantaneous acceleration of 3 meters per second squared down the incline. So is it speeding up or slowing down? Yeah, if velocity and acceleration are in opposite directions, it's slowing down. If they're in the same direction, it's speeding up. And we want to know, what are the instantaneous angular velocity and angular acceleration vectors? So with these kind of problems, just always choose a coordinate system with the x-axis along the incline. And so the velocity of the center is equal to, in this green coordinate system, what are the components of the velocity of the center? 2, 0. And that's equal to negative omega times r, which is 0.1 meters, and then 0. So omega, using the x equation, is equal to negative 20 radians per second. And so as a vector, the angular velocity vector is 0, 0, negative 20 radians per second. Any questions about that part? And then same idea for the acceleration. The acceleration vector of the center is, what are the components of that? 3 meters per second down the incline. Yep, negative 3 meters per second squared, 0. And that's equal to negative alpha times 0.1 meter, 0. And so the x equation says alpha is equal to positive 30 radians per second squared. And so the angular acceleration vector is 0, 0, 30. Any questions about that one? Okay, let's do one that combines rolling without slipping with some other relative motion. Okay. Okay, so let's say we have a cart. With a Ferris wheel type thing on it. And let's say this is the point P. And we're going to figure out what's going on with this point P. Let's say the wheels have a radius of 0.1 meters and angular velocity vectors of 0, 0, negative 3 radians per second. Let's say this Ferris wheel thing has a radius of 1 meter and an angular velocity of, the wheels are going clockwise. Let's say this thing's going counterclockwise. So 0, 0, 5. What are the instantaneous velocity and acceleration vectors of the point P? Well, I'm going to call this point C, okay? And notice that that point C moves rigidly with the cart. So we're going to use what we know about rolling without slipping to figure out what the motion of the cart is, which is the motion of this point C. And then we're going to use relative motion to figure out what the velocity and acceleration of P are based on what we know about C. So the velocity of P relative to the ground is equal to the velocity of P relative to C plus the velocity of C relative to the ground. And same with acceleration. Acceleration of P relative to the ground is equal to acceleration of P relative to C plus the acceleration of C relative to the ground. We're assuming it's 0. So this is constant, and this is constant. So will there be any acceleration? There will. Remember, because that point, I mentioned this, I think, last time. The question to ask yourself is that point moving with a constant speed in a straight line, moving in some crazy pattern, combined pattern? So there has to be acceleration. And yeah, it's going to come from the centripetal acceleration term. Okay, so these two, where are these going to come from? The acceleration of C relative to the ground. That's right. These are going to come from rolling without slipping. And these two are going to come from circular motion. Okay, so the velocity of C relative to the ground is equal to negative omega times r, 0. And that is negative 3 times 0.1. Yep. Yeah, right. You're right. So the velocity of C is equal to 3.0 meters per second. And the acceleration of C relative to the ground is equal to negative alpha times r, 0. So that's negative 0 times 0.1. So we got 0. So this is the rolling without slipping part. And now we'll go to the circular motion part. The velocity of P relative to C is equal to omega cross r. So now we're talking about the Ferris wheel thing. So omega is 0.005 R vector is this. So we have 0, 0, 5 crossed with 1, 0, 0. And you get 0, positive 5, 0 meters per second. And then the acceleration of p relative to c, all ripe watermelons will rot. This goes away because there's no alpha. And so that's equal to 0, 0, 5 crossed with the quantity 0, 0, 5 cross 1, 0, 0. And that is negative 25, 0, 0 meters per second squared. So this is circular motion of the Ferris wheel. The rolling without slipping is of the wheels. And now we can combine these. Go back to the relative motion. Velocity of p relative to the ground is 0, 5, 0 plus 0.30. And so you get a velocity of 0.3 in the x direction, 5 in the y direction, 0, z. And the acceleration of p relative to the ground is negative 25, 0, 0 plus 0 so negative 25, 0, 0. Any questions about that one? Okay, let's stop there. So next class, I don't know how long this lockdown drill is going to take, but it's going to start out like right at 10, I think they're doing it. We're supposed to, like we're all supposed to get in a corner and like shake and like pray and stuff.
I like watching parkour videos.
Oh yeah, parkour videos. Yeah, we can do that.